Oh, I got music playing. Sorry about that, folks. This is gonna get DMC'd, I guess. Hope not. Okay. Call these. Oops. Hello, everybody. I'm just kind of typing some notes. I will talk about this. I just want to include it. What I'm typing now will not be in the assignment. It also won't be on the test. But these explicit conversions are very helpful when we're coding. So I just want to include it because I did do a little bit of it last time. And I'll remind you about what I did. How are you guys doing today? Happy Wednesday. It looks like a lot of people got the assignment working, which I'm grateful for. There was some confusion. I also know that some of my instructions were pretty vague. That comment about the PID thing, where I said set the PID equal to a new PID, that was definitely a mistake on my part. I should have been more explicit, and I will be in the future. So I'm sorry about that. But for those of you that got up and asked questions, I think we got it resolved. So good on you, and just do that in the future. A lot more of you sent me messages this time. I'm very happy about that. I also see that you guys started using this class discussion channel, and I like that. I really like that. So keep doing this if you can. If you post your code, I will delete it. So don't feel bad. I know that's kind of a mistake, and you know it's kind of hard for me to say, because if the code you post is almost right, I don't want other people to just get it for free. You know what I mean? Sometimes if you post an error and there's some obvious code in there that's wrong, I guess I'll leave it, but Just be careful, and if you don't know, you just send it to me. So yeah, I think that all went over well. Any questions or comments on that? You can still turn it in late today. I don't deduct too many points for it being late. I'm sure some of you know that by now. So get it in if you can, and ask me questions if you need. We're going to talk about something very simple today. We're not going to be doing a whole lot more in regards to this address stuff. Next week we'll begin arrays, but today we're just going to talk about dynamic memory allocation. Assignment 4 is up. This assignment, we'll see how it goes. I haven't set the due date yet, but I'll give you at least a week. And today we'll cover everything that you need to know for that assignment. And I'll probably go over it at the end. So with that being said, I'm going to kind of do a quick review about what we talked about last time. So let's just do that real quick. The header, there's implementation files thing that we did for assignment 3. Most of you guys figured it out. Some people were confused that, you know, the class was, like, the prototype was in a different file than the, you know, definitions. But in the future, if you're ever confused about that, you have to make sure, first off, that all of the files are in the same directory. I'm just going to pull out an example here. I guess we'll do game and game H. Those ones are pretty simple. So this is the game H file. And you notice here that it's pretty small, right, this file? And so this is game.h. And if you look in game.cpp, notice here I say include game.h. So everything that's in this file can see. And so you don't have to bring this class into this file. All you have to do is use this namespace operator to do the definitions. So I know that might be a little small, but just once again, if you're ever confused, just look at what this CPP file includes. And if it includes this file, then it definitely can see everything in here. So we did kind of go over that briefly. It wasn't too difficult. Most of you guys got that in the assignment. If you turned it in and it compiled, obviously you figured out how this thing kind of works. And then I talked about the header guards as well. And so just recall very briefly that this says if not defined, and then some name here. So it checks the current environment to see if there's a name game.h anywhere, or game_h anywhere. And if it is, then it skips this whole thing. It skips whatever this is. It says if not defined, right? If not defined. Then it will define it, and then it will include these this header file. And so this kind of helps us get around some things. You know, if you just want to include all the same libraries and all your same files, you can put up some header guards. And that will prevent the compiler from getting mad at you from doing redefinition stuff, right? If you include string as a library twice, the compiler will say redefinition of string, things like that. So we use these header guards to kind of help us out with that. So we talked about that. Oops. Like having the background there. And just stop me if you need a refresher on any of this, or if you have questions. On the explicit conversion, I will just bring it up slightly, but this is just where we cast something to something else. And so we talked about it at the end of class last time, which was a week ago, long time. So I'll just kind of bring it up again slightly when we get started today. And then finally, we were talking about pointers and pointer arithmetic. And the first thing we started with was addressing. And so in these notes here, I've compiled all of the operators that we've used so far. So if you remember, this is the address of operator, which returns the address of a variable. It's a unary operator, and this is how we use it. And here's a small example of that, right? Where we have, this is a, I'll bring it up again today. This is a static variable, not to be confused with a static member variable. This is just a static variable, meaning that the memory is allocated before runtime. And if we print out and x, we'll get the address of that. We also talked about the dereferencing operator. Now this we'll spend a lot more time on today. Let me bring it over here. And so whatever is on the right side of it needs to be an address. And whatever type this address is, it will try to dereference that as a type. And so we'll talk about this again today with the explicit conversions. And so here you can see that we declared pointers, right? We kind of barely talked about that. If I declare a pointer and assign an address to it, I can dereference it to see what's located within that address. We also talked about these brackets, right? And the brackets are not that much different from this. It's just a dereferencing operator for arrays. Okay, so you've seen this before. And if you recall, this is where I had my on-stream fail. X is an address, right? And so if I even see out X, it will see out the address. If I see out the address of X, it will take the address of an address. And that's where I got confused. So don't do that. X is just an address. And what it does is it dereferences it. And it dereferences it at the location that is this many bytes over. I'll just bring up that equation again to remind you. But remember that these are exactly the same. Okay, so the first index here at x is the exact same of adding x plus 1 and then dereferencing the whole thing, in which we add 1 to the address of x and then we dereference the whole thing. So these are exactly the same. And then we finally talked about the size of. So recall this returns the size of a type in bytes. So you can use it with a type, size of int, or you can use it with a variable, size of, say, int x, size of x. So I gave you some examples here, right? An integer is 4 bytes. A string is 8 bytes. And a short is 2 bytes. So this is just returning how many bytes a certain type is. So we know what an address is. These are just kind of the brief notes that we did. And recall that when I'm talking about this, in the case that int, that x is an int, it will add size of int bytes. So in this case, it will add 4 bytes to the address and dereference this. If this happened to be a string, and we said x plus 1, it will add size of string bytes times 1. So this would add 8 bytes to the address. And if you need a refresher on that, just watch the video. And I gave you all these examples here, right? Here's the equation for that. And then here are all these examples. Excuse me. And then finally, we introduced pointers. So with that, we're about ready to go for today. Please let me know if you would like to talk about something. So what we're going to do here is this. We're just going to say addresses and pointer arithmetic here. And then down here, we're going to add a section. And this is just going to be pointers. The introduction to pointers and dynamic memory. So let's go ahead and get started. So here I've got my favorite super simple C++ program, right? This is just one int main, no header files, none of that. Just one file. And if you remember how to declare a pointer, we type some type here, right? Let me see if I put it here in the notes. Say I said type var name, so I guess I should do this. So this is our syntax, right? In which we include this little star. If you're not confused yet, this star is used to declare a pointer, it is used to dereference a pointer, and it's used in multiplication. This is a very versatile character in C++. And so it is just a variable that holds an address. So if I ask you, what does a pointer hold? It holds an address. And pointers have types, right? And what does the type tell us? The type tells the compiler how to dereference the address, right? And so we'll have a little example of this where I'm going to do some explicit conversions, dereference, where I do some explicit conversions, right? If I scroll up here, you can see I just kind of talked about that. I'll do some explicit conversions, and I'll show you how we can make the compiler dereference addresses as different things. So, how many bytes as well, right? And a good example of what's the representation, is this a string or a double? Because a string is 8 bytes and a double is also 8 bytes. So we got a good question here. Macros says, do pointers allocate memory when declared? The answer is no, and we will learn how to do that today. Now this is the most dangerous thing that we'll ever do in C++. Now, if you're coding on your own Mac, this is where I'd be careful. I would highly recommend you use Bobby or Sally. We're also going to learn how to use Valgrind today to help you find memory leaks. So, yeah, that's a great question. Let's just jump right into it. So this is, let's just declare an int x. And we're going to put some comments in here, right? This is a static variable, as I said not too long ago, which means allocated, we'll say memory is allocated before runtime. And so when we do something like this, the compiler says, all right, I'm going to need this, I'm going to need an integer. And so what it does is before any of the code is run, it automatically will generate code to request memory from the operating system. And then at the very end of our code, it will put a delete statement to return this static memory that we used back to, back to the operating system. So, I'm going to tell you why do we need dynamic members, right? So why can't we just use this? You may have experienced this before, and this is mainly why we use vectors. So when we do this, when we say int array and declare this, this is a static array. And if it's static, it cannot be resized. Looks like my face might be in the way here, maybe not. So this is why we use vectors in general, because if we want, it's an easy way for us to make arrays that will resize. You know, we can add to it, we can delete from it. But what you'll find is that a vector is a class, and in the constructor and the destructor, and in the pushback method, however those are implemented, they are using dynamic memory allocation. So we use pointers mainly for dynamic memory. So what does that mean? That means during the runtime, memory is grabbed from the heap. Now this is different from the stack. We won't get into that yet. Okay, we're fresh computer scientists. We'll learn more about this later. Memory is grabbed from the heap. I guess we'll say grabbed, allocated. And static variables do this before runtime. So what do we need to be able to allocate memory during runtime? We need some operators to do that. So let me grab this little thing up here. I kind of like what I did with this. So we need some operators, right? So we say, how do we do this? Allocate memory. So we only have two operators. And so this operator is called new. And the other operator is going to be called delete. Now delete is not allocating any memory, so we'll come back to it in just a moment. And I'm going to delete this stuff. So these are the only two new things that we're learning today. So what does new do? New allocates memory into a pointer. So that's exactly what that does. New must take the same type as the pointer. So if we say this is an int pointer, I guess we'll do some syntax, right? So we'll do the generic syntax first. Generic syntax says, make this a little bigger, I think. Generic syntax says we've got type, and it's a pointer, right? So we've got a pointer of some variable, and then we'll say variable is equal to new type. So what does that look like in an int? And now we're going to run it in the code so we can see what's going on. So if we said int x, and it's a pointer, right? So we got to include that little star there. Whenever we're ready to allocate something into this, we're going to say we're just going to say x is equal to new int, right? Does that make sense? You can just kind of interchange these two things here. So, I guess I'll kind of put this down below. Kind of like what's going on there, but we need to do other stuff. So I'll even show you. Let's just start with this. Let's make an int. This is a pointer. And let's actually just see out what's in it. Excuse me. So let's get our feet wet again. So at this point, no memory allocated. Though we have allocated static memory for an address, But let's not get too confused here. I didn't pull up my MOBA. Silly mistake by me, but I do need a tea break anyway. Wow, that's hot. Okay. It's loading. We'll press zoom here a million times. Then I hit unzoom. Making more work for myself. Working on my actions per minute. All right, here we go. So here we are on Sally. I'm going to go into my test directory because I love my test directory. I guess I'll leave that in there. And let me go to my lessons folder. We're going to pull in this file. I called it switching for some reason. I can always rename it. So we're just going to see what is in this address, and we're going to see what we can kind of do about that. So I'm going to G++ this file, switching. Let's see what we get. So it compiled, of course it did. And notice here it says 0. Okay, so it seems that Sally has initialized this to be 0. Now 0 is equivalent to null. And have you guys ever, I'm screaming at you, have you guys ever had a seg fault and been very confused at why you have seg faults? Well, we're about to learn how seg faults happen. So I'm going to try to dereference this. Now, do you guys agree? Yeah, we're going to learn about seg faults right now. Do you guys agree that there's no way to know what will be initialized in this value? Now, as C++ becomes more regulated, they may initialize this always to 0. But chances are I just got lucky here, okay? I just got lucky, and there was a 0 value already in the address memory that this is using. Chances are it will just pull, the static memory will be allocated, and it will just pull some random location in memory, and the memory may contain some garbage value, right? I know some of you experienced that if you did not initialize your record count in assignment 2 and just started incrementing away, you might have ended up with some negative value, and that's because you ended up with some garbage value. So we're going to do this, and this is always good to do. So I'll put it in the notes. Initialize pointers to null. Now, you don't always have to do this, but there's nothing wrong with it. Okay, so we should always initialize our pointers to null. You also may see null pointer. It's the same thing. Okay? Same thing. I like using null, but that's just because I'm a database guy. And I am familiar with that term. So, talking about pointers here. And I made this a little bit. Let me just see if I full screen this to make it look better. How do we do this? And I just want to put here. So, can anyone take a wild guess? What happens if I try to dereference a null pointer? I gave you some foreshadowing, so I think that you might be able to figure this out. So where's my syntax? I guess we'll say varname equals null, or varname equals null pointer. We segfault. That's exactly what happens. So let's make this program segfault, okay? So this is initialized to null. I'm going to put the dereference here. Okay? And I'm going to load this onto Bobby or Sally here, and it's going to segfault. And now we're going to learn about why you might have segfaults, because I know plenty of you had segfaults in your first assignment. I didn't see, you guys did a great job kind of cleaning your stuff up on the second assignment, so I'm happy about that. Segmentation fault. Okay, so what did I tell you? That's what happened. We dereferenced a null pointer. Whoop. So, in assignment 2, let's just kind of remind you here. Let's do a little fun example. Let's say we've got some array or vector, right? So we've got an integer array, and say it's only got 3 elements in it. And it'd just be a 2, maybe a 6, and maybe a 16 or something for fun. So this is our integer array. Now recall, what are these indexes at? All right, so this index is at the 0th. This index is at the 1, and this index is at the 2nd, right? And so many of you would do something like this. And I'd pay attention, because if you didn't see me make a comment about this, if you're doing a for loop and you say I is less than something, well, let's go backwards, right? So if we traverse this array backwards, we want to start at something like array.size, right? Now this is an array, it doesn't have a size. So if we say int, whoops. If I say int size is equal to 3, which that's right, the size of it is 3. We know this, but we cannot index it at 3. So if I say something like this, int I is equal to size, and then I say I is greater than or equal to 0, and then I say I minus minus, right? And then somewhere in here I say cout array located at I. So recall that I cannot index this array at 3. And so let's pretend we know what the addresses are, right? So this array is located at some address. This one is at the very beginning. This one is 4 bytes over. And this one is 4 bytes over. And so this one, we actually can only go 8 bytes over. And as soon as we do this, we go over 12 bytes. So in memory, we probably have these pointers, right? And what is contained within the pointers? Well, we've got probably an address. We've got an address. We've got an address. And then we've got a null there. We've got a null right there at the 3rd index. So that's at the 0th index. This is making sense, right? This is at the 1th index. This is at the 2. And now there's nothing here. This is at 3. And so what if we got some garbage value here? Instead of being null, it was this. Your program would work. And sometimes it does, right? Sometimes it does work. And that's because this memory wasn't cleaned out or anything, and we just got lucky. But then there's some garbage program floating around in your garbage program. There's some garbage value floating around in your program. But if this happens to be null, as soon as you dereference this array at a null address, segfault. Does that make sense? So if you're segfaulting on your program, look at these things. Where are you indexing this array? You're probably out of bounds. You're probably out of bounds. This is a fun file. I think I'm going to save it, clean it up a little bit. It's a good example file, right? And we'll make a new one. And we'll go to our new now. Now we're going to allocate some memory into our stuff here. So this is going to be, I don't know, we're just going to start with n. And I'll rename them before I upload them. I'll just grab my favorite stuff in this file. I always like to have return 0 at the end, though you don't need it in main. But notice it is an integer function. I always like to make sure I'm returning integers. So, what did we have? We had a pointer, right? So here we go. So we know that that'll cause a segfault. So now we should allocate memory into this thing. And so can anyone tell me what I need to type here to allocate memory? I'll put a little cout statement. And then, yeah, we're going to do a few things. Right. Yeah, you do have to use new. I was hoping that you would give me the full thing, but that's okay. We got to say pointer equals new int, right? So that's how, yeah, whoop, yeah, fair. We're all new at this, right? So pointer equals new int. All right, so now we've allocated this memory, and now we can see that we're going to have some address here. So we're going to even cout. I love doing the cout statements, right? So we'll cout this null value, which will be 0. And then we'll do like a little program statement here, right? Allocating memory. And then we're going to see that now we've got this address. We've got an address in this pointer now. So let's pull it in. View, zoom. You can do it, Sally. I believe. All right, so here we are. Boom. We're gonna compile that. We're gonna run it. Notice here there's the null address, right? That makes sense. And it says allocating memory, and after I've called new, now I've got an address. Now I've got an address in that pointer. Now there's one thing we didn't do here. We didn't clean it up, but we're not gonna get there yet. So how do we start using this, right? Can anyone take a guess? I haven't told you guys yet. If I wanted to store an actual integer in here, how I might do that? Or how's this? Let's do it this way. Please tell me if this is okay. So I've made an integer pointer. I then allocated an integer of memory in there. And now, don't look at this, okay? Now I say I want 3 to be stored in there. Can anybody tell me why that's wrong? And Red Rose here says, yes, he says, so that's how you do a linked list. An endless stream of pointers linking to the next. Yep, and we'll learn about linked lists. It's just pointer, 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 pointer. Linked lists are not contiguous in memory. So I think if you remember from last class, contiguous in memory is side-by-side memory. Linked lists are not side-by-side. But yeah, Red Rose got it again. So if we want to store an integer in this address, we have to dereference it first. So dereference address to store value. Dereference address to store value. Does that make sense? Now this calls a constructor. I just want you guys to note this. This calls a constructor for an int value, okay? Now ints are kind of primitive types, so maybe it doesn't call a constructor here, but later today we'll do an example with a class. And you'll see that we're going to be calling a constructor on this new call. So we have to dereference it to store values in there. Let me put the notes in here. Well, we'll do it after. I'll have to clean this up, of course. So, now I'll ask you this. Now, let's say I do some more code down here. And then somewhere in here, I say pointer equals null. So now we're going to talk about the delete and stuff. Now what this is called is, this is just called memory leak. So what I did was I allocated the memory. Just doing plenty of comments here. Here I allocated the memory. And then I overwrote the address. Now I can't access it anymore. And so memory leaks are probably going to be the bane of your existence for the next few weeks. But if we pay attention now, we can do it. So this, as soon as I allocate an address into this pointer, it becomes almost dangerous because now I have memory in my hands. And if I do anything like this, where I overwrite it, it's lost forever. I've lost that address. And now that memory address is still in the computer. The computer thinks that it belongs to this program, but the program no longer has access to it. And so the program cannot actually return it to memory, and memory thinks it belongs to the program. So it's like you lost memory. It's kind of wasted memory. Your computer may have some processes that kind of go in the memory and clean it up. Most likely it does. But if you're worried about that, let's use Bobby and Sally, okay? Let's not do this on your local machines. Visual Studio Code, or not Visual Studio, Visual Studio IDE will be okay for that. It kind of wraps everything up in a shell. So what we're going to do now is I'm going to show you how to, first off, delete memory, and then second, we're going to see if we've got any memory leaks that are going on here. So here's the delete statement. And this will deallocate, that's the term that we like to use, which returns memory, I'm going to say dynamic memory. Don't try delete on static variables. Returns dynamic memory back to the OS, the operating system. So we'll do some syntax here. So after we've allocated something, then we'll just type delete var. That's it. So now we're going to run valgrind to help us find this memory leak, and I'll show you kind of how these things get cleaned up, so you know how to fix your programs when this happens. So what does valgrind do? Valgrind is a program on Sally, Bobby, that tells you where your memory leaks are. You should compile differently. And the compile statement is the same as normal, except you're going to add a -G. Now, I helped a few of you with your programs already where you did have seg faults, and I asked you to run this statement. So this will be in your notes, and you should remember it. But we're going to type, mess that up. We're going to type G++, myprogram.cpp or whatever it is, right? We could have file1.cpp, file2.cpp. We also have to do this thing, right? And at the very end, I want you to add a -G. Add -G to compile statement. Now for you nerds out there, what this does is it adds debug symbols in the code, in the object code. Right? Your compiler takes your C++ and it turns it into object code that the machine understands. And when it does that, it loses line numbers and it replaces everything with addresses. What does the debug symbol do? Makes it so we can see the line numbers. Okay? Makes it so we can see the line numbers. And then how do we run valgrind? Very easy. We're just going to type valgrind --leak -check equals full /a.out. So let's do that now, and I will show you that this program here has a memory leak. Now, the reason it has a memory leak is not because of this. Well, it is because of this. But it's also because I never had a delete statement, right? So probably before I return 0, I want to type delete pointer. And actually, before I overwrite the address, I probably want to type delete pointer first. And we'll get rid of it here. So here I end up deleting the pointer before, and I'll define what a memory leak is in the notes, so we can keep this clean. So don't worry about that going away. I'll write that all down. But here we're going to delete the pointer, and then we'll set to null. If we don't do that, and then we pull this code onto Sally, let's do everything that I just told you to do. And you will see that we have a memory leak. So I'll take my regular statement, and I'm going to add -G at the very end of it. Okay, that's all I have to do. And then when I'm ready to run it, I'm going to type valgrind -- leak - check equals full ./a.out. Okay. When you run it, you'll see that it says memcheck memory error detector. And it's going to take a moment to run your program. And it kind of wraps it up in this thing here. So you can see here, it tells you who made it. And then you can see this is the output of our code right here in the middle. This is the output of our code. And then it tells you, kind of here at the end, it says heap summary. It says how much memory was in use at the time that the program exited. You can see 4 bytes in one block, right? Does that make sense? So let's look at this. 4 bytes, right? Does that make sense? Yes, it does. Integers are always 4 bytes, right? Integer is 4 bytes. Integer is 4 bytes. And that's how much was in use at exit. And it says here 4 bytes are definitely lost. And then look here at the very end of this, it says this. It says n.cpp, so that's the name of my file. It says line 11. It says line 11. Whatever this memory is, it didn't get deallocated. So when we go look here and look at line 11, look exactly what's on line 11 here. It says the new int. So it's telling you how this memory was lost. Or it's not telling you that. It's telling you which memory was lost. So this program will not tell you like when the memory was lost, right? If I had overwrote it, it wouldn't tell me that. It just tells you that this is not getting deallocated. This thing here is not getting deallocated. So what do? I add my delete statement. Let's even add a little fun thing here. This is deleting memory. Or deallocating, right? It's a term we like to use. When we drag it in here, we'll compile it, we'll run with valgrind. And you'll see here at the very end, it says all heap blocks were freed, no leaks are possible. So you always need to see this message. So does that make sense? That's how we use valgrind. And I'll use it plenty of times in the upcoming weeks. All you need to know for the upcoming homework is these things here. The deletes in the news. And so now we're going to go into our next example, probably our last example for the day. And let me talk about the memory leak errors real quick. Well, memory leak, we'll define that. It's memory that is not returned to OS. i.e., address was overwritten or address was never deleted. And in fact, if the address was overwritten, it can never be deleted. So that's what a memory leak is. Now we'll talk about some other problems. But the first thing we'll do is open a new file, and we're going to make a class. Are there any questions so far? You guys are following, right? I know this is not the most engaging example, not a super real-world example, but we're just kind of learning how memory works in C++ from the most basic building blocks. So what we're going to do is we're going to make a class here, student. And I'm going to kind of copy some stuff over here because you don't need to see me type this out all the time. Let's see what I got going on here. And I am going to change some things up. We're not going to do this static thing. We're just going to do these. So privately We'll have their first name and their last name. And then we're going to have some public member functions. Recall here your object notes, right? This is a constructor. This is also a constructor. Notice that this constructor is taking parameters. And so that the parameters probably go with these things here, right? This is probably the first name. This is probably the last name. This is probably the GPA. And this is probably the student's age. And then here I've got a constant print student function. Recall that this is constant because it is not going to change this object. I'm going to save this, probably new one for now. And let's just kind of add some things here. This is a good refresher, okay? So if you're not, if you had some trouble with this assignment in constructors, maybe just pay attention real quick. This is going to be our default. As always, I do this. I'm going to shorthand the end line here. Okay, that's an end line character for those of you who don't know. I see plenty of you using those, though. That's fine. And how do I, if I want to initialize these values, right, I can do it in the body, or I can just put a colon here, and I can say, hey, the F name is going to be initialized to an empty string. The L name is going to be initialized to an empty string. The GPA will be initialized to 0.0. Make sure that you spell it right. And lastly, I'll say that the age is initialized to be 0. Okay? That's the default constructor, right? If I want to do the parameter constructor, very simple. I even just copy paste it here. I know that I don't like to do this normally, but I'm going to bring this down. I have to give these names, so this is probably going to be FN for the first name, LN for the last name, float for the GPA, and A for the int. And I just have to replace these in here, right? So the FN goes in there, the LN goes in there, the G goes in there, and the A goes in there, right? And so now all of these values are being initialized. And this is our parameter constructor. And then finally in our print student function, I'm just going to copy this one over because I like to have this big cout statement here. Okay, so it's just a pretty way to print our student. Makes sense so far, right? We've got a class. And I just really quickly put in those constructors and this one function. So in main, we can make a student pointer. And I'll show you some other memory things that are going on. So what have we learned so far? We're going to make a student pointer. This will be a pointer. And we should initialize it to null always. Because right now it's not doing anything. And to save us from memory leaks, I prefer that the program segfaults than anything. And now when I'm ready to allocate the memory, step 2, allocate. We call new, right? What does that look like? That looks like pointer is equal to new student. Now I said this calls a constructor, right? So this literally is the constructor call. You know which one this one calls, right? Of the two constructors we have, which one will be called here? We'll have a second one. Equals null. The default constructor, exactly. So this one calls the default constructor. Why is that? Because there's no parameters, right? There's no parameters in this thing. Does it look like we pass any parameters to this guy? No, it does not. So it calls the default one. Whoa. If I want to fix that, let's give it some parameters. Hey, I want this student to be named John Doe. I want their GPA to be a 3.5. And I want them to be, say, age, I don't know, 19. Okay? So this calls the parameter constructor, right? And so now pointer has an address. Now here's where I ask you to use your brain. And a student now. Can anyone tell me the code? Let's say I want to print student. I want to call print student. How do I do it? How would I call print student from pointer 1? So I have the pointer 1 here, and I've got print student somewhere. I want to call this somehow, but I have to do a few things first. Normally, with an object, right, we've got obj. That's the object. With the dot operator, and we call print student. But this is not going to work on the pointer, right? Because the pointer is an address. So we kind of have to do something fancy here. Right? This will not work. This says address. Okay, it's even telling me that this is not good. It says address. Dot operator print student. Does not look good. It's okay. I'll give you just a few more seconds and then I will give it to you. Hint, we need to dereference this somehow. Step 1 is to dereference. So let's do that. So now this has been dereferenced. And then now, it's still not going to work because of the order of operations. Precedence, right? You know, in multiplication and addition, multiplication always happens first. In this case, the dot operator has precedence over the dereference operator. So the dot operator is going to try to dereference this thing first. Or no, it's going to try to call print student from the address first, and then it will try to dereference the whole thing. How do we fix that? With parentheses, right? Does that make sense, what I did? I dereferenced the address, and then I used the dot operator to call a member function from the student. There's one thing I'm going to add while you guys are thinking about that. Let's pretend we've got a destructor in here. This destructor doesn't have to do anything other than goodbye, student. Thank you. Thanks for saying yes. So step 1, we dereference it. And number 2, we print student. There is a shorthand way for us to do this, and I'll show it to you in one moment. But I just kind of want to show you everything that we've learned so far. At the end, I should delete my pointer 1. I should delete it. Just so we can clean up all of our memory, and let's just see that this works. And then I'll show you the shorthand way, and then I'm going to show you some problems that we can have with the memory. I also want to include this in the notes. Like I always do, I'll clean it up at the end because things get kind of wild here. Operators, we'll do Valgrind later. So we'll just say how to access member functions / variables from within an object pointer. Step 1 is dereference. Step 2, dot operator. What does that look like? Syntax, very easy. We put the object in here. We dereference it. This is an object pointer. We dereference it, and then we call the dot operator, and we say member function. Something like that, right? So it's probably on Sally now. We're not going to run Valgrind because I know that I don't have any memory leaks yet. And then we'll run it. Let's see what we got. We called our parameter constructor, right? That makes sense. We said new student, called the parameter constructor. And then here's my nice little print statement, John Doe, 3.5, age 19. And then it says, goodbye, student. Now I'm going to show you that if I print this at the end, we still have the address. That's a very good question, right? So Aaron asks, when you delete the memory, does the destructor go off? And yes, so that's, yes, exactly. So that's exactly what happens. So I'm putting this C out here to show you that when we call delete, the destructor will be called and not here, right? Because normally the destructor is called when it goes out of scope, right? But in this case, we call delete. So here we'll say destructor is called. And then we'll see that we still have this address, actually. We still have this address. I like to have these allocation stuff, right? Allocating. Let's see out, you know, pointer is equal to pointer 1. After we allocate it, we'll print out whatever that is again, then we'll print our student, then we'll delete it, and then we'll see out what the pointer is again. And we'll run all this code, and we'll kind of just walk through it real quick. Yeah, I love this. Aaron, you're nailing it today, man. Yes, we still have the address. Do you see a problem with that? Do you see a problem with that? There's totally a problem with that. You're thinking like a true C++ warrior here. All right, so we initialize this pointer to null. We printed it out here, right? There's a 0 sitting there. We allocate our memory, and now look, we've got an address. We called that parameter constructor, right? We've got our student. And then I called delete, right? So we said goodbye, student. And then I print out the pointer again. And guess what? I still have this address. I still have it. So I can do some kind of bad things, actually. Is there anything wrong with this? Let's try it. So what did I do here again? Will this work? I'll ask you the question. Will it work? Assuming that this will print this same statement. What do you think? So I returned this. I gave this address back to memory. You guys say no. Well, you might be surprised. I said, here's what I said. I said, hey, this address, it's okay to go back to memory when I call delete. And so the operating system claims this address. Isaac says, yeah, let's go see. So operating system claims it, says this is mine again. But the program still has that address. It still has the address. So there's nothing stopping it from causing havoc. I need to get rid of that slash. I don't know why I keep doing that. Ooh, very interesting. Man, I wish it worked. Maybe we'll try with an int. Okay, I'll give it to you guys. Aaron and Red Rose, you got it. I'm sad, honestly. Maybe I can make it work with a different pointer. But here's what I'll say. Do you agree with me that just because that it looks like when we call delete, by default, it kind of like set that address back to something in there got set to 0, right? Because you can see, look what it did. It called, it kind of worked, right? Do you see here that it printed this thing? And then it tried to maybe dereference the f name. So here, let's come back to this one here, and I'll show you. If I don't do this, let me try to see out pointer dereferenced. So in this case, remember that now we're just dealing with an integer and not a complicated object. I bet that it'll print out the 3. But here's the issue. So while I'm compiling this, I'll talk to you about what's going on here. Is that we still have this address, and because we still have this address, we can still use it. We can put stuff into it. But remember that the operating system now thinks that it has this address again. It still thinks that it has the address. Interesting. Okay, it looks like it erases it. The delete statement erases it, but I'm going to change that. Hey, I want this to be 4. I want this to be 4. So we still have the address here, right? We deleted it, but we didn't set it to null. I'm going to assign 4 to it, and I'm going to try to print it out. Notice we didn't get a segfault there. So your program is working with no compiler errors or anything. It's just working with an address. Look. There's a 4 in there. I put 4 in an address that the program no longer has access to. So imagine this. Imagine this. We call delete on this pointer. Now what we have here is if we don't set it to null, we have what's called a dangling pointer. That's a good question. Red Rose asks, what exactly is the delete command doing then? Delete says this. Let me see if I can include it. It returns, I like what you say this. So it does return. In other words, I like to do this IE here. It says OS, you can use this again, kind of thing. So all it says is like, the program says to the operating system, I am not using this address anymore, so you can use it again. That's all it does. As soon as you call new, the operating system reserves that address, and it says, all right, I'm not going to give it up then. You have exclusive control of this address. And as soon as I call delete, the operating system says, all right, I'll take this address back, and I'll do whatever I want with it. So imagine somewhere down here, I say pointer2 is now equal to new student. Does it make sense? I'll kind of show you an issue here. So there's a dangling pointer in pointer 1. And I called new student here. And the OS may now give us back the same address that it did before. Yeah, exactly. That's exactly what's going on here in this one. Is that even though the memory is given back to the operating system, we still have the address. So we can still do stuff with it. But we cannot guarantee that we'll have this for forever. I can't spell guarantee. I'm a computer scientist. I think... is that an E? Don't judge me. Well, I have Google. We cannot guarantee this address, this will stay for, is what I should say. I know this is getting kind of confusing. We're going to spend 2 more days on this stuff, okay? So we're just going to have to kind of think about. But here, let's say OS may give us back so since we deleted this, when we call allocation again, the operating system may return the same address back to this pointer. And then somewhere down here in the code, I say something like pointer1 equals, let's say I override it with a different student constructor. It doesn't like that. So say somewhere down here, I dereference pointer 1. I assign student into it. And now pointer 2, whatever was in there got killed. So this is how we'll finish off our last example for the day. And I'm just going to show it to you because these kind of things we will see on the test. And we'll keep this very simple. We've only got a few minutes anyway. And I'll even give you some practice problems for the test. And by the way, for tests, I'll always give a review sheet. And I'll give answers to the review sheet a few days later. And tests are also on Web Campus, and you don't have to use Lockdown Browser. So there's no way I can tell you not to use your notes. But more on that later. So let's say we've got int pointer 1, and we've got pointer 2. I know this doesn't look right, so we'll do it this way. You have to include the star with every name if you want to list them off like that. And say pointer 1 is equal to a new int, right? So now we're going to allocate our memory. And then we'll say pointer 1, we're going to dereference it. We're going to put some value in there. So now pointer 1 contains this. Is this legal? Looks like it, right? And so look at this. This is the last thing I need you guys to like kind of wrap your head around for today. So we put just 4 in both of those pointers. So if I see out pointer 1 and I see out pointer 2, we should see the same number, right? So we'll run that code real quick, and then I'll leave you with one more question. And then I gotta rework those notes and upload everything. I didn't want to compile that one. I think we called this N2. So we see that those are both 4s, right? Why is that? Because, and this is really what you should pay attention to for assignment 2, okay? You'll be kind of swapping pointers around. You're playing with addresses. So even though we had only one memory allocation here, now we have what's called an alias. And I'll put this in the notes. This is an alias. So today we talked about, yes, very good. Sibe, you're so right. There's nothing wrong with doing this. There's nothing wrong with doing this. We're being safe programmers here. Safe programmers. Thank you for reminding me. We'll assign these guys to null because we want to be safe programmers. So notice here I only did one allocation. I assigned it, and then I gave it an alias. So we talked about memory leaks today. We talked about dangling pointers, and now we're talking about aliases. These will all go in the notes. An alias means that this contains the same address as this now. Right? And so when I dereference this address and this address, they're the same address, and we get the same value. So now I ask you the question. I come to pointer 2. I dereference it, and I say, hey, this is equal to 72. And then I see out pointer 1. What is the value? It's not a trick question. What is the value of pointer 1? Notice we put 4 into pointer 1, and we put 72 into pointer 2. 72. Exactly. Yes. They are the same address. They're 100% the same address. And so does it, and here's another question for you while I'm compiling it. Does it matter I delete both of them? Or how's this? This will cause a problem. Can anyone tell me why this will cause a problem while I'm compiling the code? I'm going to comment them one out because I just want to prove that it's going to be 72. But why is that an issue? I want to know if you understand the C++ addresses. What's going on here? What do these variables contain? Right, there you go. 72. They're both 72. Yeah, exactly. That's exactly what's happening. This is the same address. So here we say, hey, let's see what the program does. It says, hey, you can have this address back. And then I say, hey, you can have this address back. But then it's going to be like, you already gave me this address back. You're not allowed to do that. So let's see what C++ does. It might segfault. That might be something that happens. Do you see here it says double free and aborts? So it didn't segfault. It says double free, right? I tried to delete the same address twice. But they're in two different variables. And this is why life is hard. And so what should we do? In general, aliasing is something you won't do. You're going to kind of do it in assignment 1, but as soon as we do this, we should probably say something like pointer1 equals null to verify that only one pointer will contain the address at a time. So that kind of wraps up our discussion for today. I'm going to just hang out here for a few minutes. Like I said, I have to clean this up, but I'm going to talk about what a memory leak is. I'm going to talk about what a dangling pointer is, if you just kind of want to watch me do it. And then I'm going to talk about an alias. You can ask questions at this time if you have any. Office hours will be at 1 in 15 minutes. Yeah, thanks for coming to the stream today. I'll say that all in a second. You're free to go if you want, but I'm just going to finish this out. So a dangling pointer is not setting pointer to null after delete. So that's what happens there. Aaron says, I'm a little confused on why when delete was called, it got set to 0 as well without null. Are you talking about in this section here when, let's see, when I called delete and then I tried to print student like this? I guess that works, right? Where I had called delete and then yeah, okay. So what happened here was most likely so this is a data type. And so this class student, the object itself has an address, and the first name and the last name also have an address, and the GPA also has an address, and the age also has an address. And so when I deleted the student, what happened when I returned it to memory was that these addresses got deallocated. These kind of look like static. Notice that these aren't pointers, right? These are kind of static things. And so when the destructor was called, it probably erased the addresses for these 4 variables. And so in fact, it printed this first line, right? And then it tried to dereference the first name and it segfaulted. Does that make sense? I know that was, it kind of got me too. I was a little worried. I kind of wish that it worked. But my guess is that the destructor kind of just nulled out these addresses. And even though we still had the address for the student, these addresses were all null. Yeah. And so it still tried it, right? It still printed this line. It still printed it. But then as soon as it dereferenced that first name, it was like, I can't do that. It's gone. I don't know where it went. And like I said, we'll spend some more time on that. But that was a great question. Thank you for asking. So we have address in program that OS thinks is free. Okay, so that's a dangling pointer. And then lastly, alias is 2 pointers contain the same address. And that's it. That's class for today. And I'll just reiterate real quick for assignment 1. You only have to really know this kind of stuff that's going on here. The news, the deletes, and aliasing. So we're just kind of playing with addresses and stuff. I didn't cover it today, but there is a video, and I will cover it on Monday. I'll at least run it a little bit in the terminal for you guys to see. So ask questions if you need. I'll see you guys next time. Thanks for coming to the stream. Office hours are in 10 minutes or so.